The vast expanse of space is not empty. It is teeming with clouds of gas and dust. These clouds, known as molecular clouds, are the birthplaces of stars. Imagine these clouds as cosmic nurseries, filled with the raw materials needed to create something extraordinary. These clouds are predominantly composed of hydrogen and helium, the most abundant elements in the universe. Gravity plays a crucial role in this cosmic drama. It draws these particles together, slowly at first, but with ever-increasing intensity. As the cloud collapses under its own gravity, it fragments into smaller clumps. Within these clumps, the density increases and the temperature begins to rise. This process marks the first step in the incredible journey of a star's life. Think of it as a cosmic dance, with gravity leading the way. From these humble beginnings, a majestic star will eventually emerge. It's a testament to the awe-inspiring power of nature, even on a cosmic scale. As the cloud fragment continues to collapse, the core becomes denser and hotter. This hot, dense core is known as a protostar. It's not quite a star yet, but it's well on its way. The protostar is shrouded in a thick cocoon of gas and dust, which obscures it from direct observation. However, we can detect the protostar's presence by its infrared radiation, the heat it emits as it contracts. This heat is generated by the immense pressure at the core, squeezing the atoms together. It's like when you inflate a bicycle tire, and you feel the pump getting warm as you compress the air inside. The protostar continues to accrete material from its surroundings, growing in mass and temperature. This process can last for millions of years, a mere blink of an eye in cosmic terms. As the protostar gathers more mass, its gravitational pull increases, drawing in even more material. It's a delicate balancing act between gravity pulling inwards and the outward pressure generated by the heat at the core. Eventually, the protostar's core reaches a critical temperature and nuclear fusion ignites, marking the birth of a star. Once nuclear fusion begins in the core, the star enters what's known as the main sequence, the longest and most stable period of a star's life. Our own sun, a yellow dwarf star, is currently in the main sequence, happily fusing hydrogen into helium in its core. This process of nuclear fusion is the engine that powers a star. In the intense heat and pressure of the core, hydrogen atoms collide and fuse, creating helium and releasing an enormous amount of energy. This energy is what makes the star shine. The main sequence is often referred to as the star's adulthood, because it's a period of relative stability and balance. The outward pressure from the nuclear fusion in the core perfectly counteracts the inward pull of gravity. This equilibrium allows the star to shine steadily for millions or even billions of years, depending on its mass. Our sun, for example, has been in the main sequence for about 4.6 billion years and has roughly 5 billion years left before it moves on to the next stage of its life cycle. As a sun-like star exhausts the hydrogen fuel in its core, it begins to evolve off the main sequence. The core, now mostly helium, contracts and heats up, causing the outer layers of the star to expand and cool. As the outer layers expand, the star's surface temperature drops, causing it to turn redder in color. This stage marks the star's transformation into a red giant. Imagine our sun, 1,000,000 times larger than its current size, engulfing the orbits of Mercury and Venus. It's a sobering thought, but one that highlights the dynamic nature of stars. As the core continues to contract, the temperature rises further, eventually reaching a point where helium fusion can begin. Helium atoms fuse to form carbon and oxygen, releasing another burst of energy that temporarily halts the core's contraction. This helium burning phase is considerably shorter than the hydrogen burning main sequence phase. For a star like our sun, it lasts for a few 100 million years. But even in this relatively short period, the red giant phase has a profound impact on the surrounding planetary system. As the helium in the core of a red giant is depleted, the star's core contracts again, becoming incredibly dense and hot. The outer layers, no longer held by a stable core, are expelled into space in a slow, gentle outflow. This ejected material forms a glowing shell around the dying star, creating what is known as a planetary nebula. These nebulae, despite their name, have nothing to do with planets. They were named by early astronomers who, observing them through rudimentary telescopes, thought they resembled giant planets. However, they are actually the remnants of dying stars, a spectacular display of cosmic recycling. Planetary nebulae come in a variety of shapes and sizes, from simple spherical shells to complex and intricate structures. These shapes are influenced by factors such as the star's rotation, magnetic fields, and the presence of companion stars. These glowing shrouds of gas and dust are relatively short-lived, lasting only a few tens of thousands of years. However, during their brief existence, they enrich the interstellar medium with heavy elements, seeding the galaxy with the building blocks for future generations of stars and planets. At the center of a planetary nebula lies the remnant of the red giant's core, a white dwarf. This stellar ember is incredibly dense, packing the mass of the Sun into a volume roughly the size of the Earth. A teaspoonful of white dwarf material would weigh several tons. White dwarfs are incredibly hot when they form, with surface temperatures exceeding 100,000 degrees Celsius. However, they no longer have any nuclear reactions taking place in their cores. They shine simply from the residual heat left over from their former glory as a star. Over billions of years, white dwarfs slowly cool and fade, eventually becoming black dwarfs. These hypothetical objects, no longer emitting any light or heat, would be incredibly difficult to detect. White dwarfs represent the final fate of our Sun and all the other stars of a similar size. They are the stellar embers, cooling down over eons, their story a testament to the cyclical nature of stellar evolution. While Sun-like stars end their lives relatively peacefully, stars much more massive than our Sun meet a far more dramatic demise. These stellar giants live fast and die young, their lives culminating in a spectacular explosion known as a supernova. As these massive stars exhaust their nuclear fuel, they undergo a series of increasingly energetic fusion reactions in their cores, forging heavier and heavier elements. This process continues until the core is primarily composed of iron. Iron is the most stable element in the universe, and fusing it requires more energy than it releases. This creates a problem for the star because the outward pressure from nuclear fusion can no longer support the immense weight of the star's outer layers. The core collapses in on itself in a fraction of a second, triggering a shockwave that rips through the star, blasting its outer layers into space. This explosion, a supernova, can briefly outshine an entire galaxy. The fate of the core after a supernova depends on the mass of the progenitor star. For stars about 8 to 20 times the mass of our Sun, the core collapses to form an incredibly dense object known as a neutron star. Neutron stars are only about 20 kilometers in diameter, but they can pack more mass than the Sun. Their density is so extreme that a teaspoonful of neutron star material would weigh billions of tons. For even more massive stars, the core collapses completely, forming a black hole, a region of spacetime where gravity is so strong that nothing, not even light, can escape. Black holes are some of the most enigmatic objects in the universe, and their properties continue to fascinate and challenge our understanding of physics. These exotic objects, neutron stars and black holes, are the remnants of the most violent and energetic events in the universe, a testament to the power of gravity and the extreme conditions found at the hearts of dying stars. Section 9. The death of stars, whether through the gentle expulsion of planetary nebulae or the violent explosion of a supernova, is not the end of the story. These events play a crucial role in the cosmic cycle of life and death, enriching the interstellar medium with the elements necessary for the formation of new stars and planets. The heavy elements forged in the cores of stars, and those created during supernova explosions, are scattered into space, eventually becoming part of new molecular clouds. These clouds, enriched with the building blocks of life, will eventually collapse and form new stars, continuing the cycle of stellar evolution. Our own Sun and solar system are products of this cosmic recycling process. The elements that make up our planet, and indeed ourselves, were once part of long-dead stars. As Carl Sagan famously said, "We are star stuff. The birth, life, and death of stars are not isolated events. They are interconnected processes that drive the evolution of galaxies and the universe itself." Understanding these processes helps us to comprehend our place in the grand cosmic scheme, a humbling and awe-inspiring thought. If you enjoyed this video, please help us out by giving it a thumbs up. Be sure to click on one of our other videos that are on your screen now.